the fungal story, we talk about, some of you may have heard of Paul Stamets. They call him, he's a mycologist. He's the world's most famous mycologist. And what's interesting, mycologist is a specialist in fungi. What's interesting is that, as a career, you try and find a new fungal species, and some people have found 4 and 5. Paul's found 237 new fungi species, and how he achieved that is a really interesting story. You can watch his story on Netflix. It's called Fantastic Fungi, and part of that story covers the life of this man. But how he did it is pretty weird. He took a hero dose of magic mushrooms, which is a paper bag full of mushroom. I mean, I wouldn't have the guts. I got a degree in psychology, and I used to work in what used to be called mental asylums and are now called mental wellness institutes or something. It's just like rubbish dumps are now called recycling centres. But anyway, there were so many people that had taken mushrooms or taken LSD that actually threw them into the psychotic state that they never, well, while I was there, they never recovered from. So I just think you've got a lot of guts to do that. But most people don't have that happen, but some people do. I would never take the risk, but some people do. He did. He was a blithering lunatic for 2 days. And when he came out of it, he could communicate with fungi. Now, you can say bullshit, but he says, I walk into a forest and I get a little message, I'm over here. And there's a new thing. You can say, oh, that's absolute crap. Well, he's found 238 new fungi. No one's ever done anything slightly like that ever. So something's happening that's pretty bizarre. And he's gone on to have the most successful company. I interviewed him at one point, and he described, he's got a thing called 10 Ways Fungi Can Save the World, and you want to watch it. It's a YouTube clip. It is tremendous, the potential of these things commercially. But he talked about this tornado that had gone through and blown these massive oil tanks, big standing oil tanks full of oil, blown them all over and contaminated several acres, several hectares with oil. So the powers that be, the people who owned the thing, wanted to clean it up and were obliged to clean it up with the EPA. Of course, the EPA doesn't exist because Trump just closed it down, but, that's the Environmental Protection Agency. They brought them, they insisted that there be this cleanup. So you had your trial area and you come in with your backpack of whatever chemicals that help break down oil. And there's 12 people that were chosen for the trial, and whoever won it got the contract. It was quite a lucrative contract. And everyone's there with their backpack spraying their various chemical concoctions, and then you cover it in black plastic. And then you come back a few weeks later and they measure who was most successful and they win the contract. And he was last to arrive, and he walks through and they're saying, where's your backpack? And he's got just this little paper bag. And he walks in and starts scattering this, and they think, who the hell's this lunatic? Then when it comes to the test 6 weeks later, he was last in the line because he was last there, and they're pulling it back, and some are successful and some have got smells pouring out of them halfway there or not doing the job. And everyone sniggeringly, it's a nice word, sniggeringly walks to his patch, and they pull back the plastic, and it's oyster mushrooms just smothering the entire thing, overlapping each other. And they test the oyster mushrooms, no at all residues of the oil, and 0 oil in the soil. It ate the whole lot as a carbon source, took out the chemicals, and you could eat the mushrooms. He won the contract, obviously. So there's multiple stories like that. It is really, really worth listening to. He's got 2 or 3 books, but his YouTube clips are something very, very special. But talking about fungi, so they're much more mobile than bacteria. Bacteria, it's this tiny, 50,000, 500,000 on a pinhead. I mean, they're tiny, tiny things. And they can move 6 micrometers in their entire life, which is, you can't see 6 micrometers. And that's all. And you say, well, how do they move around the field and do things in different places? They use the rest of the soil food web as their bus. They hop on the back of a nematode, good and bad. They hop on the back of a microarthropod, these little invisible insects. They hop on an earthworm. They'll join onto a fungal hyphae and then hop off when there's some work to be done. So it's really important that the rest of the soil food web is kind of intact. But fungi grow 40 micrometers in a minute, and there are single fungi that cover like hectares of land. And Paul Stamets refers to the underground internet, that you can put your foot on one of these huge fungi, it's one species, and the message is on the other side, someone's coming. And that's the internet, that's the Earth's internet. It's very much the same process. And it's absolutely fascinating to look at this thing now that there's so much research called the mycorrhizal network, and this recognition of this communication that's happening. And it's really fascinating in some instances. For example, a mother tree, the tree in the forest, her seeds drop and they're carried by birds. Sometimes they drop beneath her, within her drip line. And very often they're 100, 200, 300 metres away because some bird picked them up or the wind blew them. And that mother knows exactly, via the mycorrhizal network, exactly where her seeds are, her babies. And sorry, I should get some water. And so the internet is based, of course, on information exchange very rapidly via that concept. This is hard goods as well as information sharing. So you can actually move nutrients on this network that covers an entire field. You can move carbon, and that's exactly what the mother tree decides to do. You're in the base of a tree, you've got to have sunlight to photosynthesize to make carbon, and you've got no sunlight. So how the hell are you ever going to go anywhere? So she directs via the mycorrhizal network some of her photosynthase and gives them to a baby. Who would have thought? So continuing with the story, they produce a substance that can digest very hard to digest things. So they take the fibrous material, and miraculously that should digest their own chitin-based cell wall, but it doesn't. No one knows why. You can imagine if the whole network, if you've got your fungal component, this is little pathways as these things die off to get oxygen in and CO2 out, to have that gas exchange happening more efficiently, and moisture and so forth can follow those tiny microscopic pathways if you've got that fungal component. Now, the acid they produce breaks the bond between calcium and phosphorus, so it's a tremendous concept. There are new research about the power of mycorrhizal fungi combined, and Hugh Lovell was so determined to make that point clear, that the most powerful biological relationship in the soil is this combination of mycorrhizal fungi and azotobacter. And they act like this really nice synergy, because azotobacter, of course, are fixing nitrogen, and they nestle in beside, they actually right along, basically living along the mycorrhizal threads. And the mycorrhizal fungi, of course, is releasing acids to make phosphate in that little zone soluble. And to fix this, it's an enzymic process. You've got to have phosphate to make ATP. So you've got this constant sort of water-soluble phosphate, which it never stays soluble. It's tying up with things all the time. So you've got this soluble flow, and you're taking that phosphate. And the mycorrhizal doesn't want to take all of its protein from the plant. It's going to suck in. You've got to grow out to 10 times. That's a lot of protein. So the azotobacter gives it protein, and it doesn't have to suck from the plant. So it's this lovely. So you want to try, as a little test, and I'm going to teach you later how you can brew your own azotobacter, which makes it really, really cost-effective. But mycorrhizal fungi and azotobacter together on a seed, try with and without and watch what you see. It is really, really special. They really, really do work really well together. So fungi tend to reduce the pH of the surroundings. How do you feed them? They like, thank you, they like long-chain sugars. So they love kelp and they love humic acid. And weirdly, some of them, usually molasses is a thought specifically as a bacterial food, but Trichoderma really likes molasses. Really good study by the DPI in Queensland looking at Fusarium on bananas in North Queensland. And they're saying, okay, well, Trichoderma can control Fusarium, but we want it to last longer on the leaf doing that job. So they followed my, I call it sending the team off to work with a lunchbox, and we talk about humic and fulvic being, humic and kelp being two foods specifically for fungi. So they do use both those, but they also use molasses at varying rates, and they found that at high rates, 20 litres of molasses with Trichoderma sprayed on the leaf had by far the longest longevity. It was just a lot of molasses, 20 litres per hectare foliar sprayed, but that gave this ongoing protection for 5.5 weeks. So it's a really good strategy. Trichoderma do like molasses. So you can feed bacteria if you want to stimulate them up with just sugar or molasses. Molasses is a really underrated biostimulant. You usually don't want to use more than about 10 litres a hectare, but wonderful really nice response you get from it because it stimulates particularly bacteria so effectively. So it's, 60 cents a litre. It's a pretty cheap response. A lot of people have discovered it, but a lot of people have yet to discover it. So fungi, kelp, humic. Aloe vera feeds both fungi and bacteria, and that's why we like to use it. So there's mycorrhizal. See, it's not hard to think it might be good. There's the original root, and that's the extension, this huge extension of tiny filaments that gives you 10 times more surface area. So all the things the roots are doing can be 10 times. Now, this is a mycorrhizal fungi. This is a treated plant that has made the roots, fed the roots, and grown the roots bigger. You can't actually see these things. You've got to dye them and put them under a microscope. They're so fine. But that's the result of mycorrhizal fungi, that extended roots. Now, there are two types. There's ectomycorrhizal fungi and endo. Endo is 90% of all plants, so it's almost everything. But pines and some hardwoods, they have this different type of fungi called ectomycorrhizal that don't burrow in and become sort of like a parasite, except they give more than they take. They just wrap a web around the root and do similar things in terms of helping the plant, but without actually colonizing the plant. So endo is most things. And the only two things that don't colonize are chenopod's, interestingly. We mentioned that's everything in the beet family. It's spinach, amaranth, and quinoa. So it's a small little group. But they don't have mycorrhizal colonization. And no brassica has mycorrhizal colonization because they produce biochemicals that mycorrhiza don't like. So that's just, it's a lot of plants. So we talked about that information superhighway called the mycorrhizal network. So much research happening on it now. But there's some really interesting things. And there's the bloke who came up with it. And there's Paul, the genius, mushroom genius. So passionate about all the many things you can do with fungi. But there's some, the benefits. I mean, you're going out, you've got this extension, so you can go and get these really immobile minerals, and the two most immobile are phosphorus and zinc. So that's, really cool delivery for those two minerals. You can drive those hyphae into clay platelets and mine the potassium out from inside the clay platelets. So that saves you some money on potassium. You break the bond between phosphorus and calcium, so you're delivering calcium to the plant. You've produced 3 biochemicals to stimulate immunity. You cannot have, so the most expensive of farm chemicals are the root knot nematodes, and the nematicides are the most expensive, 3,000 a hectare for methyl bromide back in the day, but the new ones are no less costly. So really expensive. And here's what you need to know, that you cannot have root knot nematodes and mycorrhizal fungi on the same root. It's impossible. You want a nematicide, you colonize with mycorrhizal fungi. You cannot have the two. They create a biochemical that nematodes can't handle, and so you want a nematicide, you get colonization happening, which is hard if you're using a lot of fungicides in your program, but you get the mycorrhizal on there, and you will not have the most destructive of all crop pests is root knot nematodes. They take more profit than any other single pest. So you'll spend your $3,000 a hectare perhaps to knock them out. But of all the things they do, the big one that makes them the most important single creature on the planet, and you think that's a big statement, was the discovery by Dr. Sarah Wright in 1996 that mycorrhizal fungi, the one most common strain called the Glomalin strain. Sarah Wright, she discovered that the Glomalin organism, which is in every soil in the world, well, the 10% that still got mycorrhizal fungi in them, produced this sticky carbon-based substance called Glomalin, and she didn't know how important her finding was, but since then we realised that these organisms, that substance is a triggering mechanism for 30% of all the humus in the soil comes from that one substance that triggers humus building in the soil. So it's a hell of a finding, and that's what makes them the most important creatures, because we need to put the carbon, 2/3 of which is now in the atmosphere, thickening the blanket, we need to put it back where it came from. And in that context, every person should be subsidised to put mycorrhizal fungi, and then sort of subsidised not to kill them off, or encouraged not to kill them off after you put them back there. But it's so important because 30% is what we need to pull out of the atmosphere, and one creature can do it. That makes them hugely important. Now, I met this bloke, Professor Ren Zhen Zhang, when I was lecturing at the South China Agricultural College. Interestingly, I was there and I was eating in their cafeteria, and I asked for a knife and fork, and a bloke came up to me and said, "Do you realise you should never," it was another professor, "you shouldn't be eating with those things." And I said, "What do you mean?" He said, "They actually they do something like ionising the food that changes the nature of it, and that's why they use wooden chopsticks." Well, I hadn't heard that one before. Anyway, the South China, well, I didn't know that he'd done the studies, but what he did was take tomatoes, which very commonly succumb to alternaria, that disease, that brown spot that moves up the plant and eventually kills the plant prematurely. And what he did was basically set up the situation where some plants were colonised and others weren't. And then he introduced alternaria and saw the difference. And what he found was that the plants were messaging via this network, alternaria is coming, prepare your biochemical suite to fight it off. And it was tremendously proven. And then this second guy, who I've also met at the University of Aberdeen, David Johnston, did the same thing with aphids. And he showed that the same thing, he activated some of them. Now, he cased them above ground in plastic because plants can message themselves above, plants can message each other above ground. So they had to remove that potential by covering them in plastic. They can't message via plastic. He covered them with plastic. And what he showed was that the plants that were colonised transferred the message. Yes, we've got aphids coming, so you prepared all this herbivory, as it's called, of biochemicals that fight off aphids. And that was happening on large areas via the mycorrhizal network. And as he concluded, the warning was definitely transferred via the mycorrhizal network. So you can see there might be a good thing to keep this system intact rather than poisoning it out in terms of actualising the plant's full potential to fight its own fight. So why have we lost 90% of our mycorrhizal fungi? Because that's where we're at. Tillage is really hard. It slices and dices them. Unbuffered high salt index will dehydrate the mycelium. DAP and MAP, you've got a material that's ammonium tagged to phosphoric acid. That's what DAP and MAP are. And they ionise, just like gypsum, which is calcium sulfate, ionises, and you've got calcium and sulfur. Well, you break ammonia from phosphoric acid, you've got raw phosphoric acid. There's nothing hotter. Well, there is, but not many things that are hotter than phosphoric acid. So if you watch under a microscope, when that happens, the phosphoric acid just sizzles up mycorrhizal fungi like putting a blowtorch to human hair. And nematicides, really harsh. All mycorrhizal fungi are killed by nematicides. There's no nematicide that doesn't kill every known mycorrhizal fungi, and that's why they'll be banned. At some point, they'll be the first of the widely used farm chemicals to go, as we realise you're killing the most important creature that's going to fix carbon back into the soil. You can't do that if we're going to be here, if you understand the seriousness of this equation. Fungicide-treated seeds, not a very good way to get mycorrhizal to colonise Longfellows. So this the Longfellow disease, as it was called, started in central Queensland, went right to the cotton belt in New South Wales, and they called it Longfellow disease because you had this Longfellow, this stupid idea of herbiciding off everything and leaving bare ground for a couple of years or whatever period. And then you plant back into it and you get this little tiny plant. It's just like a bonsai cotton plant, goes nowhere quick. And so you analyse it, and what you find is that it's lacking phosphorus and zinc. And you say, oh, we'll put more phosphorus and zinc, and it doesn't work. You can't grow the plant because cotton plants are mycorrhizal dependent. You can't grow them hydroponically. They're dependent on getting phosphate and zinc from mycorrhizal fungi. When you killed everything, for 2 years, mycorrhizal don't care who's there. They colonise with everything except for those two plants that I mentioned, those two species I mentioned. And without anything there, they die off. And what it was not a disease. It was a complete lack of mycorrhizal fungi, Longfellow disease, as they call it. So, Longfellows are a terrible idea, and you don't do it. Glyphosate has now been shown to compromise, not hugely, but to some degree, high N and P fertilisers. Basically, if you've got a whole bunch of DAP under a plant, the plant says, well, why do I need you? I've got all the phosphorus, and they also are linked to nitrogen uptake. I've got all the phosphorus I need. That's usually why I give up part of my sugar to feed you. So the mycorrhizal fungi colonised and started growing, and the plant says, no, I'm shutting you down. And then, by the time your phosphate locks up 6 weeks in, well, it's only a 100-day cycle, and you just lost 6 weeks of that. And then it says, okay, maybe I'll reactivate you now, but it takes 6 weeks to grow out. And that's the end of the season. So you just blew that opportunity. So you've got to sort of somehow work around that using less DAP and so forth, or using guano, which isn't immediately soluble and so forth, so that doesn't happen. The GM BT crops, the BT cotton, they've now shown that, again, sometimes we do have to be careful with this messing around, but Bacillus thuringiensis, the bacteria that you can spray onto a caterpillar and it produces a toxin that kills the caterpillar. And they said, oh, let's take a cotton plant and several other plants internationally, but only cotton here, and let's modify the plant so it pours out this toxin. So they've spliced a BT, that bacteria's genes, with a plant gene, and they've got a plant that constantly pours out that toxin. Now, what happens in nature, and this is the difficulty when we start messing with a perfect blueprint, what happens in nature is that everything adapts. And the insects have said, all right, we'll just adapt to this. It takes a couple of generations of cotton to slowly adapt. And so what we do is keep on changing that genetic modified seed and making more and more and more of that toxin released. And we're up to 4 times what we started with of that toxin in BT cotton. And now we're killing lacewings, we're killing monarch butterflies, we're killing all sorts of things that weren't intended to be killed. And it's affecting mycorrhizal fungi on the roots, because there's so much of it. And it's not just for the 2 weeks you spray out the BT, it's the entire crop cycle is pouring out 4 times more of that toxin for the entire 4 months or 5 months of that crop cycle. And you can see that's not natural, and it's not how things are going to work as good in the longer term story. So how do you put them back? Really good idea to just put them on your seed. Now you can use in broadacre, or say this model where you say you're putting a little bit, you've got a grass species that dies off. It's not really the model, but if it was, you had a grass species that died off, this is just to give you the idea, and you want some green, and you're going to plant something like oats that'll stay green and be a green tucker during the season. As you direct drill your oats or any number of varieties of diversity into that pasture, you treat that seed with the mycorrhizal fungi. And only the little bit of seed you're putting in there, and that will slowly jump from the plant you've treated to the plant next door and colonise that paddock. And you're much less likely in a pasture scenario to be obviously tilling or using large amounts of chemicals there to kill it off. So you've sort of done the job. It's a very, very good way to do it. If you use it as a seed treatment in broadacre, you will not have full colonisation for $7, but the $7 investment to even end up with maybe 20% colonisation as well. It's usually going to cost $40 to colonise completely, but we should really be subsidised for that when you understand how important it is. Very effective nematicide. There's a research by a woman called Dr. Wendy Tahiri that's shown us that there's some plants that feed mycorrhizal fungi, and this combination of oats and crimson clover, really, really powerful. And now a new study showing that 2 other clovers can be added to that and further stimulate whatever mycorrhizal fungi or the mycorrhizal fungi you've inoculated to get more of these wonderful creatures working in your soil.